Vectors and projectiles, these go hand in hand because we're talking about 2D kinematics, which is basically everything you know about one-dimensional motion, but now we're just extending it to situations where you have something moving in 2 dimensions, and a projectile is just a typical example of that. Vector concepts, we'll talk about magnitude, direction, translation, addition, etc. A vector is something that has magnitude and it has direction. So this green vector has a particular direction or a particular magnitude, and it doesn't really matter where it is located. I can represent, for example, a velocity, even if there's an object that's, say, down here. It's apparently a little tuft of cloud. That object could have a velocity that way, but I can represent the velocity with the vector up here just as well as if I had the vector right here. So they have a magnitude and they have a direction. As long as you don't change the magnitude, which is the length of the vector. Now I'm going to deliberately do that. I just changed this vector. I just changed this vector again. As long as I don't change the length and the orientation, then I haven't changed the vector. So I can translate it. That's called translation. Now when I add these vectors, I put them tip to tail. So if I were to add these vectors that I have here, I would arrange them like this. And the result of those goes from the beginning, which is right here, to the end, which is right here. I'm representing that with this resultant vector. That red resultant goes from the beginning to the end. It really does fully represent those. And what's interesting is it doesn't really matter what order I do these in. There's a commutative sort of property. So look, if I go green vector first, then orange vector, then blue vector, you can see that my red vector still does represent those three. That's the resultant. Now these vectors can be broken down in components, and if you just look at this one here, you can see you can sort of see it suggesting a right triangle, and the components will be really important later. However, for the purposes of this course, we're not going to spend a lot of time on the mathematics of vectors. We could, but we just don't have time. There are some key examples, such as projectiles, where the mathematics is going to be really important. Now, speaking of projectiles, so what is a projectile? A projectile is something that has been projected into space. So don't think of a projectile as something that is in the hand of the thrower, or it's not the rock while the rock is in the catapult. It's the rock after it has been released from the catapult, and it is essentially in free fall because it's only under the influence of gravity. Now, some key concepts about projectiles. This is a motion map of a projectile, and if you look closely, what it really is it's a vertical motion map and a horizontal motion map combined. Look at all these vertical velocities. These guys, look at these vertical velocities, like this one. You can tell I'm drawing with the mouse, so it's hard for me to circle this. These vertical velocities. Those are the vertical velocities of a vertical motion map, and this one represents the peak where it stops vertically. But here's where first one of the misconceptions comes in. A projectile never stops unless it's thrown straight up, and then it's not projected horizontally at all. There's got to be some horizontal projection for it to be a true projectile. So it doesn't stop up here. It just has a vertical velocity of 0. So it's hard for you to see maybe, but there's a little subscript here which is saying v sub y equals 0. So everything you know is still true. about vertical motion, and we're getting down to the essence. You should take these different positions and these different velocities and break them down. So where's the minimum? Minimum velocity? Right here at the peak, but it's not 0. The velocity at the peak is the horizontal velocity because that's the only component that it has left, because the vertical is 0 there. Where's the maximum? Well, the maximum you can see is at the very beginning and the very end. It's the maximum velocity because that's where the vertical velocity has the greatest magnitude. And what about the horizontal velocity? Well, look at all these horizontal velocities. These horizontal velocities are all constant. Well, that makes sense. That makes sense because, of course, they're constant. Gravity doesn't pull it horizontally, so it's just going to move at constant speed. And we're assuming no air resistance, just like in free fall. The only influence here is g, which is gravitational acceleration, which is downward, so it should only influence the vertical velocity. So the vertical velocity is ever changing, and the horizontal velocity is constant peaks. The horizontal acceleration is 0. So speaking of acceleration, where's the minimum acceleration, the maximum acceleration? These questions don't really apply, or they're worth thinking about, but the conclusion is it's just constant. It doesn't have a minimum or a maximum. It's always the same. It's always downward everywhere, including at the peak. What's the horizontal acceleration? 0. The x acceleration is 0. The y acceleration is downward, always, 9.8 meters per second squared, downward. This represents just before it hit the ground. This represents just after it left whatever launched or threw it. And why? Because the force of gravity acts on a projectile when it is in its path. What's really powerful about this motion map is this pretty much answers every conceptual question that you can be asked about projectiles. Pretty much all the classic conceptual questions about a projectile tend to be about its velocity, and in particular its horizontal velocity or its vertical velocity and its acceleration. So when you're doing projectile problems, you're going to be thinking about the x and the y, the horizontal and the vertical. When you're thinking about the horizontal, you want to be thinking about this equation, d equals vt. Why? For what reason? Because this is horizontal motion. There's no other kinematic equations that apply because all the other kinematic equations have acceleration in them. And for the y, there's no simple answer, but you want to think about vertical motion strategies. All the kinematic equations will apply.